Howdy. Chapter 12, Polar Coordinates. At the start of this course, we introduced the idea of unit vectors. The vectors I and j, pointing in the x and y directions, proved to be extremely useful. Think about how difficult it would be to use Newton's laws or calculate work if we did not have these vectors. But these vectors and the xy coordinate system, called Cartesian after Descartes, are not always the most useful. Consider the real force of gravity between the Earth, mass me, and some object, mass m1. The magnitude of the force, according to Newton, is g, universal constant, mass of Earth, mass of object number 1, over the distance between their centers squared. The x component of this force is F sub x minus g, mass of Earth, mass of number 1 over r squared times the cosine of theta. And the y component is similarly complicated. Since r squared is x squared plus y squared, and the cosine of theta is x over r, it is definitely a problem trying to solve for anything. This force has the feature that it always points towards the center of the Earth, but this feature is not apparent from the x and y components. What we need is a different coordinate system with its own unit vectors that will take advantage of this feature. This coordinate system is called polar coordinates, and here the position is given by r, the distance from the origin, and theta, the angle that the r vector makes with the x-axis. The unit vectors are defined as I sub r, which points along the r vector, and I sub theta, which is perpendicular to IR in the direction of increasing theta. The entire chapter is devoted to deriving the components of the velocity vector and the acceleration vector in this coordinate system. It involves extensive use of calculus and may not seem terribly exciting. Believe me, you will find it very rewarding to be able to derive the expressions for the IR and I theta components by yourself. Knowing this will enable you to deal with a force like gravity with no difficulty and will help you understand some sophisticated quantities such as torque, angular momentum, and the law that relates them. If this is not motivation enough, you should know that it has happened in the past that this derivation is the first problem on the third test. And history can sometimes be used to predict the future. The entire problem will boil down to finding the time derivatives of the unit vectors. Our old friends I and j were fixed in length and fixed in direction. Since the derivative is proportional to the change, and these vectors do not change, their derivatives were zero. This is not the case for I sub r and I sub theta. As the object moves around, the position vector r moves around, and the directions of IR and I theta change with time. Their derivatives are therefore not zero. You will need to use some of the things you should have learned in calculus, including the chain rule and the derivatives of the trig functions. In case you were wondering why you had to learn that stuff in calculus, now you know. In the same way, you might wonder why you need to learn this derivation, beyond the fact that it is probably going to be a problem on the next test. Have a quick look at the next 4 chapters in the book, and you will see why it is needed. Summary. A new coordinate system and the corresponding unit vectors are introduced. The entire chapter is devoted to finding the components of the velocity and acceleration vectors in this coordinate system. Don't leave home without them. Gig 'em.